computer. Okay, so for today's class, okay, so yeah, we first kind of a little bit review the reaction of your chapter 11, okay. And if you have any question, you still type in the chart window, okay. So in 11 we learned kind of actually a lot of reactions, okay. So but keep in mind, okay, most of reaction can be summarized by these three mechanisms, okay. And the mechanism one kind of just you generate kind of carbon-cation intermediate, okay. So carbon-cation kind of planar structure, okay. Nucleophile can go up or from down, okay. So in this case here, there's no stereochemistry selectivity for the mechanism one, okay. And then for mechanism two, okay, so you generate some kind of triangle intermediate, okay. So you push electron twice, okay. So and so in this case here, block here the front side of here this here arcing, okay. So nucleophile can only attack from back, okay. So that means kind of for mechanism two, okay. So that's anti-addition, okay. So that's here stereochemistry, okay. So for both mechanism one and two, okay, radiochemistry, okay. So follow Markov-Nikolov rule, okay. So electron goes carbon with more the hydrogen attached, okay, and then nucleophile goes kind of carbon with more the alkyl group attached, okay. So electron you can think about kind of hydrogens, okay. Right, mechanism three kind of totally opposite, okay. So that's hydrogen oxidation reaction. So this reaction, okay, so because this concerted kind of reaction process, okay. So we generate kind of single addition product, okay, hydrogen and also another the boron or kind of eventually the OH group add on the same side of the bond, okay. And also because the electronic kind of effect and also the steric effect, okay. So radiochemistry for kind of anti-Markov-Nikolov rule, okay. So that's keep in mind, okay. Right. Okay, so under mechanism one, okay. So we learned totally kind of actually looks like three reactions, kind of only two types of reaction. First kind of the addition of the HX onto kind of arcing, okay, which is kind of the halide, okay. And for Markov-Nikolov rule, okay, so keep in mind, okay, so the for mechanism one, okay, so we have all the possibility for kind of rearrangement, okay. So and then for the city trade bond case, you can add one equivalent kind of HX or kind of two equivalent HX, okay. And then you can also do kind of the hydration reactions, okay, just under kind of acid catalytic, and then you generate kind of alcohol, okay. So still kind of rearrangement, okay, and also because this one kind of the reversible reaction, okay. So reversible from kind of dehydration reactions, okay. So normally has very poor yield, okay, okay. Right, on the mechanism the two case, so we learn those reaction, okay. First kind of the addition of Br2 or kind of Cl2 on the kind of the arcing, okay, you generate kind of the dihalide, okay. So keep in mind the anti-addition, okay. And then for the alkyne case, so we can add one equivalent kind of the Br2 or kind of Cl2 or can add two equivalent in excess, okay. So we generate kind of tetra kind of chloride or kind of tetrabromide, okay. Right, and then we can also do some kind of this reaction kind of the polar solvent, polar process solvent like water or alcohol, okay. So in this case the water we generate kind of halohydrogen reaction, okay. Halohydrogen reactions is keep in mind, okay, so the X is kind of no electron file, okay. OH kind of nucleophile add on to kind of more substitute carbon, okay. And then we also learned kind of the mercury oxidation reactions, okay. So the oxymercuration reduction reactions, okay. So for this reaction, okay, so also generate kind of the alcohol and also full Markov-Nikolov group, okay. The good thing kind of normally has higher yield and also no rearrangement, okay. And in that case, so oxymercuration reduction reaction can be also you apply to kind of alkyne, okay. So alkyne case, so generate kind of ketone at kind of the final product, okay. The reason for that, very beginning you generate kind of eno, but because eno keto totalization, okay, so eventually give kind of ketone at the final product, okay. So that's keep in mind, okay. Right, mechanism three case, so we learn kind of the hydration oxidation reactions, okay. So this time kind of the anti-Markov-Nikolov, okay, OH goes kind of the last substitute carbon and hydrogen goes kind of internal carbons, okay. If we apply kind of similar condition to kind of the internal alkyne case, so give kind of internal kind of kind of ketone as a kind of the product, okay. So this one is keep in mind, okay, so still follow anti-Markov-Nikolov rule, okay. So and then followed by kind of keto totalization, okay. So that's why it gets kind of the ketone product, okay. if the kind of terminal alkyne, okay, so yeah, you have used a little bit of bulky kind of the boron reagent, okay, so yeah, that's the amyl kind of yeah, boron, okay, so that can give kind of aldehyde as kind of the product, okay, so that's the first reaction kind of transgender kind of aldehyde, okay. Right, and then we learned a bunch of oxidation reaction and also reduction reaction. For here, you have to try to memorize their kind of the reagent and also what's their product, okay. So first one kind of epoxidation case, so we normally use kind of the peracid case as kind of the reagent case, so MCPPA case, so we kind of epoxide case. And then next kind of the hydroxylation reactions case, so we use osmium tetroxide case or kind of the together with kind of sodium and the sulfite case, you can kind of diol case. So for this reaction, you can also use kind of these two reaction conditions case. So potassium permanganate case or kind of osmium tetroxide with kind of the T-butyl hydro the peroxide case. Right, and then for these two reactions, epoxidation and also the hydroxylation case, so both kind of single addition product case. And then last kind of oxidation reactions kind of the ozonolysis case, so we use ozone and then CH3K, SH3K, so that's here cleave the C bond into a 2 CO bond case, so that's here keep in mind, okay. Right, and then we learn some kind of reduction reactions, okay, so yeah, first one kind of the catalytic hydrogenation of alkene, okay, so this one single addition, keep in mind, okay. Right, and then we learned three kind of the hydrogenation reaction for the alkyne, okay. So if we still use kind of catalytic hydrogenation reaction conditions, okay, so that you give kind of the totally saturated product, okay, won't stop at kind of cis bond stage, okay. But yeah, if you want to start at cis bond stage, okay, so use kind of the Linder catalyst, okay, so that's give you kind of cis alkene, okay. And if you want to get kind of trans alkene, okay, so use kind of sodium or lithium kind of in the ammonium, okay, as kind of the solvent, okay, so that's give kind of trans alkene, okay. Right, and in that case, we learned kind of the conjugated addition to the dyeing, okay. So that you have to keep in mind, okay, so what conditions, okay. So if normally under the cold kind of low temperature conditions, okay, that will be follow kinetic the route, okay. So and then 1,2 addition, okay, 1,2 addition, okay. Still follow Markov-Nikodym, okay. And then if it's kind of at higher temperature, okay, so that will be kind of thermodynamic control, okay. So that you give kind of 1,4 addition product, okay. Yeah. So that's the all about kind of the chapter 11, okay. And then this chart I already upload online, okay, so you can study for it, okay. But for the exam quiz, okay, so you are not allowed to use this chart, okay. So you have to memorize all these reactions, okay. So if I find someone use this chart during exam quiz, okay, so I will give you 0, okay. Yeah. Walking application. All right, epoxidation, okay, so the make diol, okay, so give you the trans diol, okay, right. Yeah. So yeah, if you want to do the ring opening of the epoxide, okay, so use OH group, okay, so you give kind of trans diol, okay, so one going up, okay, one going down, okay. And then if you do the kind of the alkene hydroxylation, okay, so the chapter 11 questions, okay, so chapter 11 question, that's give kind of cis diol, okay, so that's give kind of a little bit different kind of stereochemistry, okay. Can be turned into ketone will maximum to yes, so that's answer is yes, okay. Can be turned into ketone, okay, so that's the here, okay. Oh, no. So this one kind of the little bit different reaction conditions, okay, from kind of the alkene the oxymercuration reduction, okay. Alkene oxymercuration reduction, okay, so you have to do 2 steps, okay. But for the alkyne, okay, so 1 step, okay. So that's have to use special reagent, okay. So yeah, you have to remember, okay. So these two are different, okay. Although both called kind of oxymercuration reductions, okay. Yeah. Yeah. All right. So any other questions? Yeah. So make sure you understand kind of the oxidation reaction kind of product are different, okay. So the epoxidation, okay, so you generate kind of epoxide, okay, and then use kind of the per acid, okay, and then the diol you use kind of osmo tetroxide, okay. So that's different product. Okay. All right, and make sure work on your homework, and those if you have any question, you can ask me kind of during the office hour, okay. All right, so if there's no further questions, okay, so we start a new chapter, okay. Aromatic kind of the substitution chapters, okay. So this chapter, okay, actually will learn some kind of reaction happen on the benzene, okay, or some kind of other aromatic compound, okay. So for the benzene or other aromatic compound, although they all have some kind of cis bond, okay, but they have pretty different kind of the properties, okay, and both kind of chemical property and also the physical properties, okay. So that's they will have kind of a different reaction from kind of regular alkene, okay. All right. And here's some kind of summary for this chapter, okay. So in this chapter, this is also kind of huge chapter, okay. So we will spend kind of more than 1 week, probably close 2 weeks, okay, to finish chapters, okay. And first you'll learn kind of the electrophilic kind of aromatic substitution reactions, okay. So that's called also kind of EAS reactions, okay. So for the benzene, okay, so we'll learn 5 EAS reactions, okay. And then based on these 5 EAS reactions, okay, we will learn kind of multi-substitution kind of reactivity and residual chemistry, okay. Yeah, so for the aromatic kind of the reaction chapters, okay, so there's no stereochemistry, no stereochemistry, because the benzene serves kind of planar, okay, no kind of chiral centers, okay. But there's kind of the lot of residual chemistries, okay. So that's the little bit KP mind, okay. Right, and then we will learn some kind of nucleophilic aromatic substitutions, okay. So here's kind of attacking species kind of nucleophile, okay. So we'll learn 3 kind of nucleophilic aromatic substitution reaction. One kind of diazonium kind of reaction, diazonium at kind of intermediate, okay. And then 2 kind of opposite kind of reaction mechanism. One kind of addition, elimination, and another one kind of elimination, addition, okay. So the addition, elimination, addition kind of you generate kind of benzene at intermediate, okay. And then we'll learn a bunch of the oxidation and also the reduction reaction for the benzene case. So like a Clemmensen reduction, Wolff-Kirchner reaction, and also catalytic hydrogenation reaction, also benzolic oxidation reactions. Okay. And for this chapter case, so different, little bit different from previous the chapters, kind of a lot of small trick, okay. And you have to memorize the case. So otherwise they easily get kind of find get some kind of mistake, okay. And so also in the end of this chapter, okay, I will do some little bit summary, okay. So and the most important and also most difficult part kind of for this chapter kind of the multi substitutions, okay. So because that's involve kind of some residual chemistry, okay, and also reactivities, okay. So when we reach there, okay, I will slow down, okay, and also I wish you guys don't miss lecture, okay. So for that section, okay. All right, okay. So let's start, okay. So we'll first kind of study kind of electrophilic aromatic substitution reactions, okay. So we will learn 5 EAS reactions, okay. So pretty much for the EAS reactions, okay. So electrophilic aromatic substitution reactions, okay. So you have benzene, okay. So I just show you guys kind of general reaction, okay. And then reactive is kind of electrophile, okay. Right. So electrophile kind of pull in electrons, okay. And then so one of the hydrogen on benzene, okay. So for example, this one, okay, one hydrogen can replace by the kind of electrophile, okay. And kind of H plus, this H plus will pick up by some other species, okay. Right, and the whole process we call kind of substitution reaction, okay. So we already learned kind of nucleophilic substitution reactions, okay. So so remember, okay, so let's say we learned kind of chapter 8. Right. So the attacking species kind of the nucleophile, okay, for nucleophile, okay, S1, S2, okay. But for here, okay, so the attacking species is actually kind of electrophile, okay. So that's why called kind of electrophilic kind of the aromatic substitution reactions, okay. Right, so here's kind of the 5 EAS reactions, okay. So we'll learn kind of the nitration reactions, okay, put NO2 on it, okay. Sulfonation reaction, put kind of sulfuric acid on kind of the benzene, okay, and then halogenation reaction, put kind of bromine or hydrogen on the benzene, and then we'll all learn kind of the free-Kraft acylation, put kind of acyl group on the benzene, and in the end, okay, we'll learn kind of the free-Kraft acylation reaction, put acyl group on the benzene, okay. Right. And for this file reaction, actually kind of there's one general kind of mechanism. Okay, so if you learn the general mechanism, okay, so that's pretty easy. Okay, so to memorize all these file reactions mechanism. Okay, right. Right. So we have benzene, okay, like this. Okay, so right, and then so benzene has kind of 6 hydrogen on the benzene ring, okay, and assuming there's 1 hydrogen here, okay, I just show 1 hydrogen as example, okay, right, and then electron file come in, okay, okay, and then the pi bond electrons kind of on the benzene kind of retrieve the electrons, okay, so in this case open the city bond, okay, and then pick up kind of electron file, okay, so pretty much like this way, okay, so like this, okay. So you pick up kind of the electron files, okay. Right, and then once you pick up electron files, okay, and then so this bottom carbon lose 1 electron, so that's become kind of positive charge, okay. Right, and then some kind of base coming in, okay. Right, pick up this hydrogen, okay. Right, and then the shared reaction between hydrogen and carbon, okay, shift back, okay, and give you back kind of the CC bond, okay. Yeah, so that's the general mechanism, okay. So please write it down, okay, because all these 5 ES actually kind of follow this rule, okay. So the only thing kind of you need to study is kind of how do we generate kind of the electron file, okay, for this 5 ES reaction, okay. Right, before we study kind of these 5 ES reactions, okay, so we first kind of understand why benzene, okay, has kind of different reactions, okay, so from kind of alkene, okay, so alkene we just learned in the chapter 11, okay, so also called kind of electrophilic, okay, so but this time kind of electrophilic addition reactions, okay, so again some electron file come in, okay, and then C bond open, okay, pick up kind of electron file, nucleophile come in, okay, and then pick up by another carbons, okay, just an addition product, okay. So why the benzene has kind of the pretty unique the properties, okay. So instead of kind of you add the electron file, nucleophile onto a CC bond, okay, so you just kind of do some substitution reactions, okay. The reason for that kind of the stability of the benzene, okay, also aromatic compound, okay. So we learned kind of chapter 16, okay, so in organic chemistry 1, okay. So aromatic compound very stable, okay, much more stable than kind of regular kind of alkene or kind of even conjugated alkene, okay. So in this case, after reaction, okay, so the compound want to get kind of more stable species, okay. So that's the aromatic compound, okay. So you can study here kind of get more idea from this kind of energy diagram, okay. So for the aromatic kind of ES reactions, okay, the first step, okay, so the first step, okay, so actually very similar to the first step of the alkene addition, okay, so kind of so the first step actually kind of exactly the same thing, okay, so the electron file coming in, okay, so open CC bond, okay, exactly same thing. Okay. The key thing comes to the second step, okay. Second step, okay, so if it's kind of alkene, okay, so nucleophile coming in, okay, pick up kind of if it's kind of the addition reactions, okay, nucleophile should come in, okay, so that should get kind of the addition product, okay, right. But for the electron kind of the philic aromatic substitution reaction, okay, second step, okay, so some base coming, okay, pick up kind of these protons, okay, give you back kind of CC bond, okay. So somehow, I will see the second step kind of similar to the E1 reaction, okay. So if you have some little bit of memory about kind of E1 reaction, okay, so some base coming kind of pick up the beta hydrogens, okay, give back kind of the CC bond, okay. All right, and so if it's kind of addition product, okay, so you just kind of this we should kind of the conjugated dyeing, okay. But if you give kind of substitution product, okay, so you resume kind of aromaticities, okay, restore aromaticity, okay. So that product is much more stable than kind of the addition product, okay. So that's why kind of the gold kind of the first addition and then second elimination, okay. So that's give kind of the eventually substitution product, okay. reason, emission driven by kind of stability, kind of aromatic. Okay? So yeah, the compound won't be aromatic, it won't be stable. Okay, so that's the reason for that. Okay. All right. Okay. So now we can study kind of this 5 ES reaction one by one. Okay. The first one we'll study called kind of nitration reaction. Okay. Right. So for nitration reactions, okay. So yeah, general reaction I showed you there. Okay. So I will draw it again here. Okay. So that's pretty much a bending. Okay. So I draw bending like this way. Okay. Just kind of circle. Okay. And then the reagent. Okay. So yeah, it's kind of nitric acid. Okay. And then use catalytic amount of sulfuric acid. Okay. So this reaction, if you done at room temperature, okay, so you put kind of only one nitro group on it, okay. NO2, okay, KP1, NO2, okay. Right, and then release one water, okay. So the sulfuric acid is kind of at catalyst, okay, so kind of get recycled, okay. Right, here I show you kind of the mechanism for this reaction, okay. So the casing kind of still hold you kind of the electron file, okay. So yeah, we start with kind of the nitric acid, okay. Right, so that's the nitric acid, okay. Right, so first kind of nitric acid react with kind of sulfuric acid, okay. Pick up kind of the hydrogen, okay. Pick up protons, okay. Right, and then similar like the alcohol as a link group, okay. So you need to convert it to a better link group, okay. So it's should be OH here, another H here. Yeah. So the OH cannot live by itself, okay. But once you pick up one proton to become water, okay. So that will be easier, okay. And then you push the electron twice, okay. Here, okay. So kick off the water, and then you generate kind of that's we call kind of nitronium kind of cation, okay. Yeah, keep in mind, okay, this nitronium cation is kind of linear structures, okay. All right, and then that's the electron file, okay. So that's the electron file, okay. And then this one will react with kind of benzene, okay. Right, so benzene, okay. Open one of the theta bond, okay. All right, so assuming we still use this hydrogen, okay. Right. Right. And then we put here NO2 on the benzene ring, okay. There's kind of the cation, okay. All right, and then falling kind of some kind of base coming, okay. So normally just kind of this water, okay. Or maybe kind of bisulfonate, okay. Okay, pick up this hydrogen, okay, and then resuming kind of the aromaticity, okay, give you back that bond, okay. Yeah, right. So that's the whole reaction process, okay. Right, and for this reaction, okay, so okay, maybe write down a little bit, okay. Yeah, if actually kind of you can control at how many kind of the nitro group onto benzene, okay. So okay. So if this reaction you don't kind of mild condition, okay. Mild condition, okay. So mild condition, okay, for example, you just kind of use pure the nitric acid, okay. Or you can use kind of nitric acid with kind of the acetic acid, okay, COH, okay. All right, and all use kind of the nitric acid, okay, with kind of the catalytic amount kind of sulfuric acid, okay, at room temperature, okay. All right, and then that's you kind of get a mono nitro product, okay. Mono nitro product, okay. And give you one example, okay. So for example, we have this benzene compound, okay, and then we do this reaction with the nitric acid, okay, and also yeah, C3COH case, acetic acid, okay. So yeah, only put here one nitro group on it, okay. Right, doesn't matter, okay. So you can put here, 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 okay. So that's yeah, the all same thing, okay. Yeah. Right. So that's a mild condition, okay. So yeah. But yeah, if you want to use a little bit of vigorous conditions, okay, so that's can give you kind of the more multi nitro substitute kind of product, okay. All right, so that's mild condition, okay. So if you use kind of a little bit of vigorous condition, okay. Right. So vigorous condition, okay, so normally use kind of still nitric acid, okay, and then sulfuric acid, okay, but here add some heat, okay. Add some heat, okay. And also a little bit more sulfuric acid, okay. Some questions? Right. So NO2, okay, NO2 here, okay, so that's NO2, okay. Nitro group, okay. Yeah. All right, do you guys got it? Okay. What on American? American is showed here, okay. Yeah. You only use the nitric acid or nitric acid is kind of some medium acid, okay, or kind of the nitric acid catalytic amount kind of sulfuric acid at room temperature, okay. So that's mild conditions, okay. Yeah. And so yeah, that's kind of vigorous condition, okay. Vigorous condition kind of use heat, okay. So and then normally you also add a little bit more sulfuric acid, okay, conjugated sulfuric acid. That's here vigorous conditions, okay. All right. So for vigorous condition, you can get kind of di-substitute, even tri-substitute kind of the nitro compound, okay. So yeah, di-nitro, okay, or kind of tri-nitro, okay. Right. Okay, and I'll give you guys kind of one example, okay. All right, so we have this toluene, okay, and react with kind of the still nitric acid and then sulfuric acid, okay, and provide a little bit of heat, not too much, okay. Nitric acid, sulfuric acid, okay, right, and then you generate kind of this compound, okay. Right. So this compound called the 4 5, okay. 2 4 5 6, okay. 2 4 6, okay. Try nitro, toluene, okay. Right. So looks like kind of very strange name, and then it's kind of uncommon comment, okay. So but if I write down it's the abbreviation, okay, so you guys will know it, okay. Yeah, that's TNT, okay. Very kind of explosive kind of chemicals, okay. And actually kind of this chemical kind of pretty easy to make, okay. So I have made it kind of when I was kind of grad student, okay. So and very easy kind of even you can do it kind of in your kitchen, okay. So but I want to show you how to do it in case someone kind of too crazy, okay. Yeah, but that's starting material product all pretty easy kind of very cheap one, okay. All right. Okay, so that's your nitration reactions, okay. Right. And then next kind of reaction is kind of we call the halogenation reactions, okay. Next reaction, okay. So halogenation reactions kind of just put the Cl or kind of the Br, okay, so chloride, okay, or Br onto the benzene, okay. And the general reaction kind of actually show there. Okay, so actually I just don't want to rewrite. Okay, so that's pretty easy. Okay, so for this the reaction. Okay, so the reagent kind of you use just keep in mind. Okay, so if you want to kind of do the chlorination. Okay, so put chloride on. Okay, so you need use the chlorine. Okay, so and then with some kind of the Lewis catalyst. Okay, Lewis acid catalyst. Okay, so most common Lewis acid catalyst for the chlorination kind of iron chloride. Okay, so FeCl3. Okay, and or you can use kind of the aluminum chloride. Okay. So AlCl3, okay, aluminum chloride, okay, both kind of very kind of famous kind of the Lewis acid. Okay. So if you want to do the bromination. Okay, so you use bromine as kind of reagent. Okay, and then this time kind of you use kind of iron bromide. Okay, right, FeBr3. Okay. So just keep in mind. Okay, so whenever you do some kind of chlorination. Okay, so keep in mind. Okay, so the counter ion for your Lewis acid. Okay, has to be kind of consistent with the kind of the reagent you want to add on. Okay, so Cl to the Cl. Okay, and then if you want to do bromination, same thing. Okay, counter ion has to be same as kind of reagent you add on. Okay. So if you want to misuse them kind of for example chlorination, I use FeBr3. Okay, so that's you get kind of the mixture. I will show you why is that. Okay, so by the mechanism. Okay, so and so that's the one thing. Okay, so next kind of show you guys the mechanism for this reaction. Okay, same thing. Okay, so we have to generate kind of the electron file. Okay, so I use the PBr3 won't work. Okay, so PBr3 is kind of noted the Lewis acid. Okay, so Lewis acid. Okay, so has be kind of there's the empty p orbitals. Okay, in the iron in the kind of aluminum kind of iron. Okay, so that's can get kind of the catalytic reaction. Okay, so PBr phosphorus has no empty p orbital. Okay, all right. Okay, so now I'll show you kind of why that. Okay, all right. So for example, okay, so here kind of the aluminum chloride case. So okay, so right, so I just kind of little bit of reverse case. So put the Cl3 before the Al. Okay, right, and then we have kind of the chlorine molecule coming in. Okay, right. So why we have to use kind of this Lewis acid? Okay, because they have kind of empty p orbital. Okay, and then lone pair electrons in kind of the chlorine can fill kind of empty p orbital on the aluminum. Okay. Right, and then we have positive charge here, negative charge here. Okay. Right, and then next step. Okay, so we have the bond between kind of two chlorine break up. Okay, and then electrons give kind of the coordinate kind of the chlorine. Okay, and this chlorine become kind of neutral, and then plus kind of the Cl plus. Okay, so that's our electron file. Okay, so 3 lone pair electrons with Cl plus. Okay, so that's how do you generate kind of chlorine electron file. Okay, right, and then falling kind of pretty similar like the nitration, also other kind of the ES reactions. Okay, and then you have benzene. Okay, assuming that still use this kind of protons. Okay, and then chlorine kind of electron file. Okay, coming. Okay, and open the CO double bond, CC double bond. Okay, pick up the chlorine, hydrogen, and Cl. So I just ignore kind of lone pair electrons. Okay. And then the falling kind of you have pick up this the H. Okay, so that's actually kind of the this part. Okay, come back. Okay, right. So this part come back. Okay, so the share the electrons. Okay, between the kind of Cl and Al. Okay, all give out. Okay, share electrons. Okay, so the bond electrons. Okay, break up. Okay, break up. Okay, and then this here actually kind of pick up this the hydrogens on the bending and then CO electrons go back kind of the aromatic kind of peak aromatic kind of the bending and then you generate kind of the another two byproduct one kind of HCl another so AlCl3 so that means kind of aluminum chloride kind of recycled so very beginning aluminum chloride activate kind of chromium kind of molecule and then recycle that. That's why kind of this one we call kind of catalyst so we can reuse kind of again and again right. And for this reaction so we can only do the kind of chlorination and also bromination so put chlorine and also bromine onto benzene ring cannot do it for the fluorine and also iodine reason for that kind of fluorine kind of too reactive so normally you get kind of the mono di and also kind of trial even kind of test substitute kind of product quite mess up and even you use kind of 1-to-1 ratio of the reagent and so if you use kind of the iodine so that's become kind of another extreme so too unreactive so even use kind of large amount kind of Lewis as catalyst so sometimes kind of if you really want to do kind of the ES for iodine so you have to add kind of oxidation reagent so and also the yield pretty poor so not the ideal one so only for chlorine and bromine you get kind of very decent yield right. Okay, so next kind of we'll learn kind of third ES reaction sulfonation reactions So for sulfonation reaction so the reagent kind of pretty easy just sulfuric acid so just sulfuric acid so the general reaction actually show there and I'm kind of draw you guys probably get again so you have kind of benzene and then just sulfuric acid so normally speaking kind of you use the very high concentrated kind of sulfuric acid so even use kind of 110% kind of sulfuric acid so 110% sulfuric acid so actually you have kind of little bit of SO3 inside right. So for this reaction so we have a common mistake so looks like pretty easy common mistake kind of students don't remember what put on the benzene ring so keep in mind you put on kind of SO3H so this one called kind of sulfonic group sulfonic group SO3 so during exam quiz so quite often I saw all kind of answer some people put kind of SO2 some people put kind of SO4H all other so remember SO3H so that's the right answer so why is that I will show you kind of mechanism and then you will understand why kind of SO3H so for this reaction again we need generate kind of the electron file first so we start with kind of sulfuric acid so that's sulfuric acid so a lot of lone pair electrons and so sulfuric acid itself kind of provide kind of the protons and in this case quickly transfer one or OH group into water right, and then that's water can get ready to leave okay, and then we push electron twice kick off the water right. And that's not real electron file so we need one more step one more step kind of just the pick up this the hydrogen So pretty much, yeah, normally speaking, just kind of some weak base like the water. Okay, so the water leave. Okay, go here, okay. So that's your general kind of real nuclear file, electron file. Okay. So yeah, sulfur trioxide. Okay. Yeah, 1 sulfur, 3 oxygens. Okay. Right, and that's the real electron file. Okay, so that's real electron file. Okay. And it's also the only the neutral electron file. Okay, so yeah, all the 5 ES reactions except the sulfonation. Okay, all other foil kind of positive charge kind of the electron file. This one's only neutral electron file. Okay, right. Why is that? Okay, because show you guys. Okay, so yeah, this sulfur. Okay, strongly kind of deficient in electrons. Okay, there are kind of 3 oxygen pull electron away from it. Okay, make this sulfur kind of pretty good electron file, even it's kind of the whole species kind of neutral. Okay. All right. So next kind of it was here. Okay. We open kind of theta bond. Okay. All right, so I just ignore kind of charge scale. So lone pair electrons. Okay, so I just but maybe add it back. There's no lone pair here. Okay, and then there's 1 hydrogen here. Okay. Okay, and then some water or kind of weak nuclear base, weak base coming in, pick up this water, and then you shift the electron back, and you give kind of back kind of the aromatic ring. Okay. Okay. We can put the lone pair electron back. Right, and then eventually, okay, so because that's kind of under acid conditions, okay, so this minus charge kind of oxygen pick up kind of hydrogen, so give kind of the final kind of sulfuric acid. Okay. So iso, okay, keep in mind that's real kind of the species build up on which kind of bending. Okay. O3H. Okay. All right. So keep in mind, okay, so SO3H, that's kind of real kind of product. Okay, so we're quite common mistake, and some student kind of put all kinds of sulfur species on it. Okay, so right, and for the sulfonation reaction, it's pretty interesting. Okay, so this is the only reaction kind of reversible. Okay, so for the all 5 ES reactions. Okay. So normally speaking, kind of if you use a highly concentrated kind of sulfuric acid, okay, so normally not only kind of sulfuric acid inside, okay, so you have kind of has kind of SO3 kind of dissolve inside, okay, so can push in kind of into the sulfonated kind of product, okay. But if you use kind of dilute sulfuric acid, okay, as catalyst, okay, so just kind of aqueous solution, okay, and then at higher temperature, okay, you can cleave off kind of sulfonated group, okay, and give back kind of just the bending, okay. So that's the very useful reactions. Okay, very useful reactions. Okay, so we can kind of apply it kind of a later synthesis design. Okay, so that's just a little bit keep in mind. Okay, so a little bit keep in mind. Okay. All right. Okay, and then we move to the next kind of the ES reactions. Okay. So that's called kind of Friedel-Crafts kind of the accumulation reaction. Okay, so that's named reaction. Okay. Yeah. So accumulation pretty much is put an alkyl group on kind of bending. Okay. So for accumulation reactions, okay, so maybe I still draw the general reactions. Okay, so we have bending, okay, and then react kind of the alkyl chloride, okay, and then use the aluminum chloride case as catalyst. Okay, so a little bit highlight this guy. Okay. AlCl3, okay, aluminum chloride, okay, as catalyst. Okay, and then you can put the alkyl group onto benzene. Okay, so that's why it's called kind of accumulation. Okay. And so Also you generate kind of here HCl as another byproduct. Okay. So for this reaction, okay, so yeah, actually kind of the intermediate kind of the carbon cation. Okay, so yeah, that's at kind of electron file. Okay, and here I show you the what's the mechanism. Okay. Right, so we have kind of here alkyl chloride. Okay. Okay. And then react with kind of aluminum chloride. Okay. Aluminum chloride case again this time as kind of loose acid. Okay. That's PMT octo. Okay, on the aluminum. Okay. And then can accept kind of electron from kind of chloride. Okay. Right. And then you generate something like this. Okay. Right. So that's negative charge. This is positive charge. Okay. And then you break up kind of the alkyl with kind of Cr bond. Okay. And then you generate kind of this is kind of the carbon cation actually kind of and then plus ArCl3 okay. Yes, plus this species okay. Right, and then this are kind of plus carbon cation okay. Use that kind of electron file okay. So that's pretty similar like other ES reactions okay. So open CO double bond okay, AC double bond okay, and then you generate kind of intermediate okay. Hydrogen okay. So this actually hydrogen pick up by the other species okay. So this guy okay. So yeah, draw that from here okay. So the bond between kind of AlCl can break up okay. Pick up this hydrogen okay. And then you shift back kind of electrons okay, and then give you back kind of give you kind of final product okay. So yeah, the accumulated kind of bonding okay. Do this that should be fine okay. Plus the HCl and also aluminum chloride okay. Yeah. So that's the whole process okay. You can see kind of aluminum chloride can actually has catalyst okay. So the whole reaction kind of get kind of recycled okay. So yeah. And for this reaction case, so you can see kind of general kind of carbon cation intermediate. That's at the electron file. Okay, so yeah, actually kind of not necessarily you use kind of the aluminum chloride okay, and then use the aluminum chloride and with kind of alkyl chloride as a reagent. Okay, any reaction as long as it's can generate kind of as long as can generate kind of the carbon cation as intermediate. Okay, so you can carry kind of the free craft acylation reactions, okay? Right. So just quickly show you two reactions, okay? So no necessary kind of so here no necessary start with kind of alkyl at kind of carbon cation, okay? So yeah, show you two reactions here. Right. So first one, okay, so instead of the alkyl halide, okay, so I use kind of the alcohol, okay. And then under the acid condition, okay, so for example, kind of I use kind of phosphoric acid, okay, right? So can also give kind of the halide, okay. So this plus sign, this contribute group, this is T-butyl group, okay. Right. Also can put this alkyl group, okay. Okay. The reason for that case, so actually we learned kind of in previous chapter case, we learned kind of alcohol condensation, okay, or kind of alcohol dehydration, okay. So this OH pick up here the H plus okay, and then you generate kind of the good link group okay, and then same like S1 or kind of the E1 reactions okay, kick out link group okay. You generate kind of carbon cation okay. So that's here the react with kind of bending okay, give you kind of the substitute product okay. So that's here the similar like the second step here okay. And another example, okay, so this time, instead of use the alcohol as starting material, okay, so this time I use kind of alkene as starting material, okay. Right. So again, I apply some kind of sulfuric acid, okay, and then also can put kind of this whole species onto the bending ring, okay. So how that happened, okay? So last year we just learned use some kind of knowledge in from the chapter 11, okay? So chapter 11, okay, talk about the mechanism 1, okay? So addition of the water or addition of HX, okay? So last year we use acid condition, the first step, okay? So this guy pick up the protons, okay? All right, so for kind of Markov okay? So hydrogen go to kind of terminal carbons, okay? And then internal carbon become kind of cation, okay? And then this one kind of react with the bending, okay? So give also kind of the similar product, okay? So that's why kind of the far away. All right, so that's why kind of this reaction can work, okay? All right, so now come to problem, okay? So so if what's the problem with kind of carbon cation at the intermediate, okay? And one can type in the kind of chart window. So we learn a bunch of reaction kind of use carbon cation at the intermediate, okay? So if that's right, okay? So rearrangement, okay? So that's one big problem for this reaction, okay? Rearrangement, okay? Right, can anyone type other kind of rearrangement reaction in kind of chart window, okay? So far we learned, okay? So include this one, we learn actually kind of totally full rearrangement, okay? So the carbon cation intermediate. Full reaction we learned so far, that's right, okay? Full reaction we learned so far kind of the can generate the rearrangement product, okay? That's right, okay? That's right, okay? So oh, you guys are pretty good, okay? So E1, S1, okay, and those the arcane addition, okay, under mechanism 1, okay. So that's actually kind of here, okay. So mechanism, so. And then here we learn kind of last one, okay. So we are totally in organic chemistry 1, actually organic chemistry 2, okay. So we only learn full reaction in what kind of the cation at the intermediate and then has the rearrangement, okay. So this one kind of Friedcraft kind of the articulation, okay. These full reactions, okay. So can have kind of carbon cation intermediate and then intermediate and then also give kind of the rearrangement product, okay. Right, so show you one example for the rearrangement of the Friedcraft articulations, okay. Right. So for this reaction, suppose we put this isopropyl group, okay, on the kind of the bending, okay, but eventually, okay, we generate kind of something like this, okay. Right. The reason for that kind of there's some rearrangement happened, okay. So this chloride gone, okay, and then actually not totally gone, okay. So you have kind of 1,2 hydride shift, okay. So generate kind of more stable carbon cation, okay. So generate kind of eventually the 1,2 hydride shift, okay. Generate kind of more stable tertiary carbon cation, okay. Something like this, okay. And that one kind of how reaction happened, okay, give kind of final product, okay. All right, I guess that's it for today, okay. So we cover kind of 4 ES reactions, okay. For the last ES reaction, we will learn on Monday, okay. All right, do you guys have any questions?